Here we are again. This is going to be about solving problems involving forces. Okay, so there's basically three things that you need under your belt, and one is Newton's laws from yesterday. If you don't understand or recognize how Newton's laws work, you will not be able to proceed to the next part, the second part, which is the free body diagram. Free body diagram, basically FBD for short. See that one? Okay, FBD for short. So, 1 second, I have to fix this screen. Stupid screen is misaligned. Somebody obviously. Okay, so free body diagram. And the third thing will be what we call net force equations. So, we know what Newton's laws are, so let's go right to the free body diagrams and see what those are. And they're really quite simple. So free body diagrams are just simple pictures to help us visualize all the forces that are involved in a situation. Whoops, I said forces. I was trying to write diagrams. Free body diagrams. So here's how they work. You basically have two parts to it. A simple shape to represent the object. And I usually use a box or something because sometimes you want to write things inside to describe the object. A simple shape to represent the object that's in the question. Or of course you may have more than one object, so you'd use a couple of different shapes. I use a box, some people use a dot or a little square or whatever, etc. And then secondly is you put arrows on there, arrows that represent all of the forces involved. Now the hard part, of course, is trying to figure out what the forces involved are. And that's where Newton's laws will help us. So I'll give you an example of some free body diagrams. Okay? So here's an example. Let's pick a situation like a car moving along at a constant speed. Okay, so we draw a little ground here, because the car will be on the ground. And there's our car. Simple box to show us the car. Now we need some arrows for forces. So we ask ourselves, what forces would be acting on a car? Well, the car itself has an engine, which is pushing on wheels, so there's a force of the car. So we'll call the force that the car makes the applied force. I use the word applied force for the thing that's pushing or pulling in the question. It could be a car's engine, it could be a dog, it could be your muscles, it could be anything. So we'll just call that F applied. Okay? And underneath here, I'm going to write down what each thing stands for so you'll remember. F applied is the force of the car in this case. And it's pushing the car forward. If a car is moving forward, though, there's also forces that are trying to stop the car. Forces like air resistance and friction with the road and so on. We're going to lump them all together, and we're going to call them the friction force, backwards, force of friction. So F with a little f beside it will stand for the force of friction. And with forces, there's all these little subscripts to remind you which one they are. There's just so many different forces. So the force of friction. Friction's kind of a neat force. It always goes against you. Whichever way you're moving, the friction force always goes in the opposite direction. It tries to stop you all the time. Okay? Of course, we also have our good old friend, the force of gravity. So we'll put an F with a little g beside it to remind us that we have a force of gravity. And at first you might think that's it, but there has to be more. And the reason we know there has to be more is if we think about Newton's laws. Newton's laws say that if something is moving at a constant speed, which this car is doing, all the forces have to be balanced. And we can see that it's possible for the friction and the applied force, the left and right, to balance. But what balances gravity? Yeah, that's exactly what it is. The ground is also pushing upwards. Remember we talked about the electrons of the ground under your feet? The ground actually can push, and it does push, and that's the force of the ground. Now this force is going to have a funny name, because I'll explain this later when we get to it. But it's called the normal force. So I'm going to write it here as the normal force, but I'm also going to put underneath that force of the ground, just so we can remember. Force of ground. Whoops, force of ground. The ground pushes up against gravity. And now we can see that all the forces do balance. So that could describe a car that's moving at a constant speed. And that's an example of what a Freebody diagram looks like. Now sometimes it will have more arrows, sometimes it will have less arrows, because every situation is unique. But we're going to practice about 5 different examples so we can understand how that works. Okay, now the next thing we said were these net force equations. What are these net force equations that I'm talking about? Well, these are just simply ways that we describe mathematically what's going on, and we break it into 2 parts. We talk about the F net x, which is going to be the total of all the lefty-righty pointing arrows. Very simple. Look for arrows that point left or right, and they're all going to be added up here. And then F net y is going to be the total of all the uppy-downy arrows, right? The vertical arrows from the picture. So if we were to write them for our picture, we would get this. F net x equals, we go up to our picture, and we look for the sideways arrows. And there happens to be 2 of them. There's one right here, F applied, and there's one right here, force of friction. So that's what I write over here. F net x is the total. So it's the force applied plus the force of friction. And it doesn't matter which order you put them in, and it doesn't really matter how they show up as long as they're in there somewhere. So it's pretty simple, right? Then you have F net y, which would be all the uppy-downy forces. So F net y. And if you look at the picture again, you look at which forces are up and down, and we go up here. There are 2 of them in this case. There's the normal force, which is the ground pushing up, and there's the gravity force pushing down. So they go together. And that's as simple as it gets. That's pretty much it. Fg, the gravity force, and the normal force. Now there is something you have to remember. When you begin to put numbers into these equations, you have to let the math know which direction the arrows were pointing. So you're going to have to remember to use positive and negative when you put the numbers in. Before you do that, you can just write them all as plus, because it is a sum equation. Okay, so that's what we mean by F net x and F net y, adding up the forces this way, lefty-righty, and up and down. So let's do an actual question or an example where we might use all this together. So let's start with, let's see here, draw a line, and we'll do an example. I have a bunch of them that I've kind of written down here. Okay, a boy pushes a sled. Actually, and I'm going to tell you that the sled has a mass of 10 kilograms. 10 kilograms is the mass of this sled. On some ice, or snow, with a force of 20 newtons. That's how hard he's pushing on the sled. Now, because it's ice, I'm going to say that the friction is negligible. Negligible. Now, some people didn't know what negligible means. The word negligible simply means that it's so small that it doesn't matter. So in this question, friction is not going to take a role. There's no friction in this question. All we want to know is finding the acceleration of the sled. Okay, so there's our question. Boy pushes a sled, mass of 10 kilograms, and he's pushing with a force of 20 newtons, and there's no friction. So what we do is we start with a free body diagram. We draw the ground, and we draw the sled. Perfect. The sled looks just like the car in the last step. What forces do we have? Well, he's pushing the sled. So that's an applied force, right, that he's applying to the sled. So we'll put the applied force here. And it really doesn't matter which direction I put it in, because it doesn't say whether he pushes left or right, does it? But we always just assume whatever way we're going is right. That's the way everybody tends to do everything. To the right, it's positive. Okay? We could do it to the left, but it just makes everything look funny. Okay. What other forces are there? Well, there's no friction this time, so I don't need to draw that in. The question says friction is not part of the question. The other thing we have, of course, is gravity. That would pull down, Fg, right? And we have the force of the ground pushing back up. But here's where Newton's laws can help me keep it simple. If I look at the picture and I imagine a boy pushing a sled, is there any motion of the sled, any acceleration going up or down? No. There is nothing happening. And the reason nothing's happening is because we know that the normal force and the gravity force are balancing each other out, so the overall effect is zero. So if I were to think about F net y, it would equal the gravity force plus the normal force. But because the sled is not accelerating up or down, there can't be any force up or down, right? So I can just say right off the bat that the net force is going to be zero for up and down. So I'm going to draw, I'm using a little light bulb as a symbol for things you want to think about when you are solving these problems. If you think about that, then we can eliminate these from the picture. And we don't even need to worry about this up or down force. There will come a time when we get better at this, when those forces will matter. But for now, for a boy pushing a sled, all that matters is the lefty-righty forces. So let's do F net x. Well, there's only one arrow in this question. So that is the only one I can put down. It's as simple as that. And it also tells me in the question how much that force is. It tells me that it's 20 newtons. So now I know that I can write 20 as the next part of this. This F applied is going to be 20 newtons. But this other side is leaving me a little bit puzzled at the moment, until I remember Newton's second law. Newton's second law says F net equals what? Who remembers? MA, right? That's Newton's second law. So I can use that here, and I can replace F net with MA. Now, of course, it's understood that since it's F net x, I'm talking about an acceleration in the x direction. But we don't have to put that. I think that just makes it more complicated. I think we're all smart enough to realize that that's what's going to happen. And I recall that the mass of the sled was 10 kilograms. right here, 10 kilograms. So I can put that in where I see m now. And so you see what happens. I get 10 times a equals 20. And the question asked me for the acceleration of the sled. And I can find it now. If I divide both sides of this equation by 10, I get a equals 2. 2 meters per second squared. Notice that when I started this, I wasn't even thinking about the a. I didn't ask myself, I have to find a. I didn't go look for a formula with an a in it to see if there was an a somewhere. All I did is follow the process. I drew the picture first, and then I drew the f net x and y equations, and out popped the a. And I'm like, yay, I got the answer. Because everything that you need will be in here. Anything that they could possibly ask you for will be here. And it'll just pop out because it'll be the last thing left without a number. So you don't have to worry about thinking how to get the answer. You just follow the process. Let's do another example. That'll be slightly different. Okay? Okay. A man lifts a box at a constant speed. Okay, when you lift things, generally we don't lift them faster and faster and faster. We lift them up nice and steady. So he's going to lift a box up at a constant speed, nice and steady, with a force of 20 newtons. Find the force of gravity. Well, it doesn't matter what we're finding. We just do it the same way. Find the force of gravity on the box. Okay, so we're going to start exactly the same process. Doesn't matter what the question asks for. We're going to start with a picture. Okay, so now we're lifting the box. So you imagine this box as it's going up in the air. There's no more ground anymore. It's off the ground, right? So we don't draw ground. That'd be silly. And of course, the applied force is the man, and that must be lifting up. That's how you lift. He must be pushing upwards this time. So his applied force will go here, up. And of course, gravity is the force that's pulling down, Fg, like this. So we draw our free body diagram like that. There are no sideways forces. When you lift something up, you push up, gravity pushes down, pulls down. There's no sideways. So this question doesn't even need sideways forces. And that's the extent of it. Which means we don't have to worry about F net x. There is none. We'll just go right to F net y. And it will be the sum of the up and down arrows. So it'll be the F applied plus the force of gravity. So far we haven't even thought about the answer or what we're doing. We're just following the process. Right? Now in this case, we have a number for how much he's lifting with. There is the force that he's lifting the box. So that is the F applied number, 20 newtons. So that goes right here, 20. The force of gravity is what we're looking for, so obviously we're not going to be able to do anything with that. And then F net y equals, according to Newton's second law, ma. It always will equal ma. Always. Now what's the problem here is I don't see anything about the mass of the box. So I can't put that in. So I'll leave it as an m. See what happens. Now, acceleration of the box. Well, what's interesting about this question is there is no acceleration because he's moving at a constant speed, which means the acceleration is 0. So that means that this a becomes a 0, and guess what? It won't matter what the mass is because anything times 0 is 0. Right? Another way of thinking about that is when you have constant speed, the net force is 0. All the forces are balanced. Right? So now I'm left with this simple equation, 0 equals 20 plus the force of gravity. And if I move the 20 to the other side, it becomes negative 20 newtons is the force of gravity. And that makes sense, because if you're moving at a constant speed upwards, your forces are balanced. 20 down and 20 up. Question? That's probably a level 2-ish type question. Okay? Level 2-ish type question. In fact, all of these today will be level 1 and 2-ish type questions, because we're just learning. Question? Well, here's the thing. You're right. What if you look at the question and you say, wait a minute, I know Newton's laws, I'm smart, I studied them. And I know that if it's constant speed, that everything has to balance. So if it's pushing 20 up, gravity must be 20 down. You could, but you couldn't just write the answer, 20. You'd have to write in English what you just thought. But that would be okay. Or you could write it, instead of writing in English, you could write it in math, which is this exact same thing. But you still need to explain why you get the answer of 20. So to answer your question, yes, you can do it that way, as long as you write down in English those statements that you've said. Okay? And you'll find that with these easy questions, some of you will be like, oh yeah, I can get the answer really fast. And you won't need to do this. But the reason I'm doing it is because this method right here will work for even the hardest questions. So if you practice it on the easy ones, you'll be an all-star when it comes to doing the hard ones. Okay? So be careful of in your head unless you really know what's going on. Okay, next example. Okay. Let's see here. All right. A ball, a 0.5 kilogram ball, rolls. Oh, sorry, it's moving first before it rolls to a stop. Well, moving at 2, I believe it was 2, no, it was 5, sorry, 5 meters per second. Rolls to a stop. Over 20 meters. So it rolls for 20 meters and finally comes to a stop. Question is, what is the force of friction? What is the force of friction stopping the ball? So a totally different question now. Force of friction. But we're going to do exactly the same thing. We're going to start by thinking about a free body diagram of a ball rolling. So here it is, and here's the ball. Same as it was before. Now, this ball has a mass of 0.5 kilograms. I like to write that right inside the box so that I can see it. Well, what's happening? Let's do our free body diagram. Is anything pushing this ball? No. It's rolling. Somebody must have pushed it before, but right now, while it's rolling, no one's touching it. So there is no applied force. Nobody's pushing the ball, there's nothing that's causing the ball to sort of move. It's just rolling because it was rolling when we started the question. So here's a question where there is no applied force. And students often think there always has to be one, and there doesn't. But there is a friction force because obviously the question is asking for it. If we assume that the ball is rolling to the right, then the friction is what's causing it to stop by pulling to the left. Friction always pulls in the opposite way to which you move. We also could draw the normal force and the gravity force, but if we remember our little idea, we know that the ball is not moving or accelerating up or down. So we know those forces are balanced, don't we? So we can right away just remember that the F net y is going to be 0 because there's no up and down acceleration of the ball. The only movement is sideways, so we can jump right into F net x. And again, I have one simple thing. The only force involved is friction. so I don't have to add any more together. And we follow the process. Again, I don't know what I'm looking for. I'm not concerned about the answer. I know that F net x will be MA, and I know that, well, force of friction hopefully will pop out. I do know the mass of the ball. It was told to me right here, 0.5 kilograms. So I can put that in for the M, 0.5 kilograms. But now I'm stuck because there are two things I still don't know. I don't know the FF, the friction force, because that's what the question asked. And I don't know the A. Or do I? What do you think? Yeah. D, right? This would be V1. Close to a stop would be V2. So we should be able to figure out an A. So we're going to borrow from Unit 1. The distance was, do you remember those numbers? So I don't have to scroll back. What was the distance? 20 meters. And it was rolling initially at how fast? 5 meters per second. And V2 will be stopped. And we want to find A. So we could use our little equation, V2 squared equals V1 squared plus 2AD. So we're borrowing our Unit 1 expertise. 0 equals 20, I'll put 5 in there so you can see where it went. 5 squared plus 2 times A times 20. And if I just keep on going down there, can't seem to go down for some reason. There we go. Down, 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 down. Then we get 0 equals 25 plus 40A. You move the 25 to the other side, it becomes negative equals 40A. Divide both sides by 40. 25 over 40 is 5/8, right? 5 over 8. And so what would that be in decimal form?
Negative decimal 625.
6 what?
25.
Decimal 625. Why is it negative? It's slowing down. That makes sense. So we know that we're right. We sense it. We can smell that this is on the right track. Now this A goes up here. And now I can finish 0.5 times negative 0.625 equals force of friction. And if you multiply that by 0.5, what do you get? 0.3 negative 0.3125-ish. Or whatever, something close to that, right? Equals the force of friction. And that, of course, would be newtons. We know that it's newtons because that's our standard unit. And now we figured out the force of friction. Why is the force of friction negative? Because in our picture, the arrow points left. Well, not because it's slowing down. The force of friction is a force. It has nothing to do with...
But it's like causing it.
You're right. The acceleration caused by the force of friction is obviously has to be the same sign. It has to be in the same direction. Awesome. All right, let's do one more example, and then I'll give you some to try on your own. Actually, I have a couple of examples. 2 more. The more we do, the better it gets. All right, so we have a giraffe pushing a wagon. At night, when the zoo is closed, the giraffes all come out and they do all kinds of crazy things, play cards, drink beer, and push wagons. And this guy is going to push a wagon with a force of 50 newtons. Okay? Force of friction that's working against him is 10 newtons. And the question wants you to find out if the wagon accelerates at 2 meters per second squared, what is the mass of the wagon? So you can see that in each example I'm looking for something different, but it doesn't matter. We don't even care what we're looking for. We don't even think about that. When we go to solve the problem, we just follow the procedure. So again, we will draw a free-body diagram. Actually, I think what I'll do is I'll pause the video for a second, let you try it by yourself, and then I'll come back and we'll take it up. Okay, so start with the free-body diagram. Here's the ground and here's the wagon. The giraffe is pushing the wagon, so that's the applied force. We'll go this way. And we happen to know how much that is, so I'll write it right on the picture, 50 newtons. And then it says there's a frictional force trying to stop the giraffe going the other way. So I'll put it over here, and we know that too. That's 10 newtons. So I'll put it here. On the picture, I don't worry about plus and minus because the arrows tell me the directions, don't they? But when I put them into the math, I'll have to remember to tell the math what those directions are with pluses and minuses. Now, what about the up and down forces? Should I even think about them? No, because remember our little light bulb, right? We said before that the motion here is sideways. So F net y, we know it's going to balance, and it's going to be 0. Because if it wasn't 0, this sled would accelerate up or down, which it's not doing. So we can kind of skip that right off the bat, and we can jump right into F net x. So let's look at F net x down here. And of course, it will be the force of friction and the F applied. And this is the part where you have to be able to watch both directions. F net x equals ma, and the friction force is 10, but it's 10 to the left. So I have to tell the math that it's left by putting a minus in there. Some of these pluses will turn to minuses for arrows that are left, right? Or down. This was the other one. And then I have 50 over here. And then I think, since we're looking for the mass, we know that the acceleration is 2. So I can also put that in where the A is, and so you see what happens. We get a nice little equation, and our mass is the only thing that's left over. I'll put it like that. 2 times m, and this equals 40. So mass is 40 divided by 2, or 20 kilograms. And out comes the answer. All right, I'm going to give you one more, and then we'll call it a day for practice. Okay. So this last one is an elevator cable accelerates a 2,000 kilogram elevator. Elevators are pretty heavy. Upwards at 0.5 meters per second squared. The force of gravity on the elevator is 19,600 newtons. What is the force of the cable? What is the force applied by the cable? That'll give you a hint as to what kind of force that is. Okay, go ahead and try that, and we'll come back in a second after you've had a chance. Okay, here we are, we're back. Then, free-body diagram. It's an elevator. So again, this time there's no ground. Students often think that there always has to be a ground in their picture. Sometimes there is no ground. And of course there's a cable which pulls up. That's what makes the elevator lift. So that's the force applied. You could call it the force of the, you can call it anything you want. Force of the cable, force, whatever. These little subscripts are just to keep track of them. So you'll have so many forces, and you can call it anything, but we'll call it the force applied by the cable. Then the other force will be gravity pulling down, and really that's it. for an elevator, no sideways forces. So it's very simple. All we have to do is just look at the uppy-downy forces, F net y. And they would be the applied force of the elevator plus the gravity force. F net y equals ma. The force applied by the cable is something we're not sure of yet, but the gravity force is down, remember. This is where I have to watch. I have to put a negative 19600. If you forget the negative because it's down, that would mess you up. You've got to watch for that. The math has to know which way those arrows point, and that's the only way you can tell it. What is the force applied? The mass of the elevator was 2,000 kilograms, and the acceleration was 0.5, so I can put those in here, and I get 0.5 multiplied, nope, backwards, sorry, 2,000 multiplied by 0.5 equals F applied minus 19600. Well, 2,000 times 0.5 is 1,000, right? F applied. And you can see what's going to happen when I move this 19,600 to the other side of the equation. It will add up to 20,600, and that would be the force that the cable would be pulling off. So in all these examples, you can see how all the questions were very different. Very, very different. They were solving for different things, but we treated them all exactly the same, followed the process, and it always comes out. The hardest part is really the Freebody diagram, because you have to think about which forces are involved, and you have to use Newton's laws sometimes to figure out which forces are involved. And that's really as hard as it gets at this point, or at this stage. Later we'll learn a little more about some of these forces we've been talking about, and we'll start using the up and down forces, the vertical forces as well. But for now, we're off to a good start.